Hello friends, we're going to extend our journey outward as far as we can today. Recall where we began. I'll share my screen and then we're going to zoom in and reconvene in the topics that we've discussed. Please recall what's called the local group. It's a tiny little group, as we'll see, of galaxies. It's just the Milky Way and Andromeda. Here's a different picture of it. Picture that is flipped, where the Milky Way is here and Andromeda is here, and we can zoom in on it and we see that there's Andromeda, there's the Milky Way, we see that there's actually little galaxies, the large Magellanic Cloud, the small Magellanic Cloud. You can see those with the naked eye if you're in Australia. You can only see those from the southern hemisphere. Same with Alpha Centauri, which is in the galaxy, of course. All stars that we see, all the stars we can see in the night sky, by the way, big deal. All the stars we can see in the night sky are in our galaxy. And with telescopes, we can see through our forest and see little fuzzy patches that are actually trillions of stars. So be careful, all the stars. So you might say, oh, does that mean Proxima Centauri is down here? No, no, no. Proxima Centauri is in our galaxy. It's really close. It's only 4 light years away. These, I think, are something like 200,000 light years away. 200,000 years away. And if you recall, Andromeda is about 2.5 million light years away. And there's actually a 2.5 million. That's right, you heard me. Light years away it takes the light to go through this space. Now, cool question is what's in between galaxies? Not much. There's no such thing as purely empty space, but it's almost as empty as you're going to get here. There's just little atoms floating around, maybe loose rocks, maybe a lone star or two, but not trillions. Stars exist in galaxies. And the universe is made of galaxies, which means the universe is made of stars. And around each star, when you form the star, is a planetary system. Please allow yourself to stretch to encompass this. There's also another little galaxy in our local group. It's pretty much 3 galaxies and a bunch of little what we call dwarf galaxies, like dwarf planets that orbit the other galaxies. There's something called the Triangulum Galaxy, little one down there. That's about, I think it's 40 billion stars, something like that. So a 1/6 the size of the Milky Way. But it's a galaxy and it's hanging out. 40 billion, nothing to shake off. And then the big one, of course, is Andromeda. That's our local group. So this is the local group of galaxies. This is what stars do. They form in galaxies. So if we continue to zoom out, we get that. Now, there's lots of types of galaxies out there. If we zoom beyond our local group, we take a telescope, we can find more galaxies. There's this galaxy. It's one of my favorites, called the Whirlpool Galaxy. It's about 100 million light years away. Or 40, I can't remember. Sorry for my numbers. But now the numbers almost seem egregious. They are important, meaning this one's still relatively close. It's only a few tens of million light years away. It's something like 25, 40, or 100 million light years away. I can't remember. It's also the Sombrero Galaxy. Looks like a sombrero. That one I think is like also 40 to 100 million light years away, somewhere in that region. Look at that one. That one's kind of fun. There's something called the Antenna Galaxies, which are some of my favorite. Look at that. Amazing. The universe does. This is what, when you zoom out, long tails. That bright thing and that bright thing are stars in our forest. Foreground stars, we call them. Foreground meaning they're right here. It's like you're looking at something in the distance and there's a light bulb right in your face. These are the light bulbs that are right in our face. They're much closer to us. This is very far away. If you zoom in on the antenna galaxies, you realize there's a lot of detail. And they are actually two galaxies colliding. This is what happens when galaxies collide. Their gas mixes together and condenses, forming new blue stars. And the blue stars explode, forming new amazing elements that your body is actually composed of. Your body won't be composed of these new elements, of course. This happened a long time ago in the Milky Way. Careful, this happens within a galaxy too, not just when galaxies collide, but galaxy collisions promote star formation. So do the density waves that move through galaxies. So galaxies are life-forming entities. They form blue stars that explode, which create the elements that then recombine into new disks and new stars, which then form planets and new life. And that process, that cycle of birth and death, occurs on this level also, and is actually essential to our existence. If you look in the distance, though, what do you see? What do you see, guys? So this is pretty far away. But you look even farther, what do you see? There's another one. There's another one. But you think that's a star? That's actually a galaxy. It's actually an egg galaxy. There's another one. All these little galaxies. Now we're going to get to the point where every dot in the distance is not a star, but every dot now is a galaxy of 100 billion stars. That probably has 100 billion stars in it. That probably has 100 billion stars, more or less, depending on its size. Some have a trillion, some have a 40 billion. Somewhere around the 100 billion mark as like a rough estimate. And some of them are big and golden. This is one of my favorite pictures because it shows all these galaxies of different types. There's a spiral one right there that's actually closer. And there's this huge golden one that's actually in the background. And these dots right here are Milky Way stars that are in the way. So there's a three-dimensionality to this that we want to sort of keep in mind. It takes a minute to wrap our heads around that. There's so many galaxies out there. Look at all these galaxies in the distance. Look at that cool one. Hi, I see you. And they're all different orientations. They're all slightly different shapes. You notice there's pretty much two types. There's the spiral ones. You see, I call them the spiral density arms. See those density arms? Those actually spiral through the galaxy on very long timescales, forming new stars slowly. Those new stars then explode and put their stuff back into the galaxy, creating new stars, creating new planets, creating new chances, opportunities for life to form. And that's the process in a nutshell. So, oh, hello. So if we continue to zoom out, we can map all these galaxies. Whoa, what's going on here? This is amazing. I'll share with you later one of my favorite pictures of all time. All these pictures are just astounding. They just show galaxies, galaxies, galaxies. This is called a supercluster of galaxies. Galaxies tend to cluster. Some galaxies cluster, some tend to stay on their own. Turns out the Milky Way is a loner. So we're actually part of a supercluster called, you might see at the top, Laniakea. Everybody say it with me. Laniakea. It means immeasurable heaven in Hawaiian. Pause, I just got chills. How cool is that? Laniakea, immeasurable heaven. It's actually measurable in terms of what it's actually doing. But the idea, of course, is gorgeous, that it's this almost unfathomable. There's a term I love, which is quantifiable but unfathomable. We can quantify and measure it, but it's actually unfathomable to picture this. So, all right, guys, find the local group. Where's the Milky Way in this? It's labeled. It's like a map. It's like find New York on a map, find Brazil on a map, find Argentina, find South Africa, find the North Pole, find the Milky Way. There it is. It's that little dot right there. Every dot in this picture is a galaxy. What shape do you see? Are they evenly distributed? No. They cluster. We call them clusters. Some we call superclusters. You might see a few. Centaurus supercluster. The Virgo supercluster is actually what we're part of. We're actually part of the Virgo supercluster. And then if you put all these superclusters together, the Hydra, the Pavo Indus supercluster, put them all together, you get a supercluster of superclusters called Laniakea. And we're part of this. And this is significant because it's gravitationally bound, which means all of these are kind of moving with each other. So they're not orbiting each other, but they're clustered together, which means they're moving with each other. And outside of this supercluster, they're going to have other superclusters that are moving with each other too. So notice we're getting huge on the scale. Every dot is a galaxy. You can Google all these, by the way, M81, M101, the Virgo, Centaurus supercluster. You can Google these, and you get a really cool picture of what these look like. Some are fuzzy because they're far away. Some are actually pretty detailed and pretty cool, like this one. I actually don't remember what this is of. I'm trying to look. Some supercluster somewhere. I don't think it's the Virgo. I think it's another one. So we're actually a part of the Virgo, but look, we're in a little gap. You see that? Did you see we're in a little gap? We're in what's called a void. So there's clusters and voids. So is there mostly cluster or is there mostly void? You see us in here's the local void, here's another void. They even label the voids because the voids are important. They're like the empty space. Nothing's truly empty, but there's really no stars. There are very, 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 very few. A rogue planet wandered out. Look, there's the local group. There we are right there. Does that surprise you? We're halfway out of the Milky Way. We're in near a void-ish space of Laniakea, near the Virgo supercluster. Did you know that's our address? It is. If we actually map these on a large scale to the farthest extent, it looks something like this. This is called the Sloan Digital Sky Survey. I remember when it came out when I was in grad school, it was mind-blowing. They mapped all the galaxies. This is cosmography. And they make these shapes. This is now a two-dimensional slice. Notice the shapes. There's voids and walls. And huge filaments is a word. Say the word filament. Filament like filaments of smoke, filaments of string. Filaments meaning long, almost string-like structures, but it's a web. You might hear the word cosmic web. This is where that term comes from. You look at this, what does it look like? It looks kind of web-ish. What word do you come up with? Come up with your own term. What does it look like to you? Maybe blur your eyes. What shape does it make? So if we zoom out even more, we see that the Virgo supercluster is there, and we start to see that all these dots are accurately shaped, accurately placed to show exactly where they are in 3 dimensions. This is a map of the universe. You might say, this took a long time to do. It did. It took decades. It's amazing how one little map you can get on Google now took decades to make. Look at that line right there. That's interesting to me. It's called the Great Wall. The Great Wall. So there's voids. The voids. Notice that the voids are actually really important. Where there's a huge void here. Imagine that space. That's bigger than I can imagine. It's unfathomable. Quantifiable but unfathomable. You can write that on your page too, like word art. Quantifiable but unfathomable. And then we can look closer at what shapes exist. So this is it in more 3-dimensional. This is the Sloan Digital Sky Survey's web page. You can go through the data. This is like a section of a 3-dimensional map. You might see it just looks like random dots, but there actually has a structure to it. And you can actually fly through it. Somebody took a few months to make this. These people did it. I don't know who those people are, but they are the people who made this movie, who took the data, and they made a fake spaceship that you can fly through all of the galaxies in the universe. Fly through the voids, There is no down. Down is inward for all of them. So number down is inward. So everything's going inward to itself. So there's no up or down or left or right in the universe. You're just floating around. There's no center. This is what the galaxy distribution in the universe looks like on the largest of scales that we can fathom or measure. It's actually easily measured relatively. Really cool techniques are used to do that. Allow yourself to fly through. I apologize that the full screen is unavailable. I will post this if you guys want to fly through it on your own. Allow yourself to be wowed by this. This is what gravity does. This is gravity. Gravity does this. Gravity creates a sphere. It creates inward. And inward doesn't just create spheres, it creates disks. But it doesn't also just create disks. On a large scale, it creates filaments. If you click in a simulation, put a bunch of gas, just a bunch of dots in the simulation, you plug in the formula for gravity, you click go, this is what happens. This is how a slice of the universe evolved from the primordial roughness in the time of the microwave background radiation. Microwave background radiation is the earliest light of the universe we can see, by the way. So this is just saying the time of the earliest part of the universe that we can actually see. And you click go. What does that look like to you? Let's watch that again. Slowly but surely forms these filaments. What does that look like to you? Does it look organic? Like life? Each dot here is a galaxy, zoomed out as far, far, far as we can fathom, or we can measure. Voids and filaments is the answer to the question. Look at this huge filament here. Look at the elegance in it. What does it remind you of? That's really, I think, important. Because the shapes on a large scale seem to mirror the shapes on a small scale. I don't believe that's coincidence. What do you feel? Please share what you find as you explore them. Isn't this amazing? This is what the universe looks like on a large scale. So this is a simulation that confirms the data in the Sloan Digital Sky Survey. This is measurement, and this is simulation. Pretty much lined up. Pretty great. It's called the Millennium Simulation. I was in college when it came out, and I was actually I didn't get it. I got it, but I was just like, this is amazing. It's taken now a few years for the significance of it to sink in. Of what this simulation showed, that on a large scale, they had computers powerful enough to process all this information, that the universe should look like this, and indeed it does. And then the Digital Sky Survey came out later, said, yep, there's a match. So we're in a really magical time of computers and telescopes of what they can do. Here's a nice picture of it. This is the simulation. So here's the progression. I'll post this too. Earth, solar system, closest stars. Let's see if I can zoom in here. These. Let's go back. I'm just going to let it load. I'll post this. It goes from closest stars to galaxy to the local group to Laniakea to all the superclusters to then the observable universe. I wanted to zoom. I'm just going back to the original view. It was taking too long. Notice the universe looks like a bunch of just random dots, but they actually have a structure. And the structure looks like Now you might say, okay, what's at the edge? Well, there's an edge of where we can see, of course. So there's an edge of where we can see, but that's not the edge of the universe. That's a hugely important thing. I would write that down. The edge of where we can see is not the edge of the universe itself. It's like if you could only see to New Jersey and you said that's the end of the Earth. Well, that's not the end of the Earth. What if you only lived long enough where light could only get you that far? Now that's a fraction of a second from New Jersey, but the universe is clearly bigger than it is old, meaning we can only see, here's the number, 13.7 billion light years outward. But the universe is bigger than 13.7 billion light years. Isn't that an interesting irony? That it's bigger than we can see. So every day, every second, we can see a little bit farther, but kind of have to wait billions more years to be able to see more of it. Happens to be expanding too, which is an interesting, very fascinating part. Oh my gosh. So those parts of the universe we eventually won't be able to see ever. If it were closed, we would obviously see the same galaxies in more directions. We would even see ourselves. That would be amazing. If you looked in the distance in one of those pictures, you're actually looking at the Milky Way. If it were closed, we would see ourselves. We don't. We don't see the same thing, and you would see it in more than one direction, as we know. So you won't, but we don't see that. So we know it's not closed on our scale, but again, if you can only see it in New Jersey, you might think the Earth is flat. You wouldn't know it's actually curved all the way around because it's way too big. So when people say the universe is flat, it's based on the observation that when we look out in all directions, it seems flat. It seems not closed. But that doesn't mean it is or isn't on large scales. So that's the journey. I hope you enjoyed it. I will be posting this and all the links. Please to write everything you observed and pause to become that space of the web of all things at once. That shape, and feel that shape evolve into that mesh, the filaments and the voids. The voids become more voids and the filaments become more dense, but it's not just a black hole, it's actually this amazing elegance. Feel that, and please talk to yourself as a part of it, because we are not in the universe. We are the universe, observing itself. Namaste.